What if you could encrypt your entire workflow state with a single line of code, keeping sensitive data secure even when persisted to disk? We'll see how to wrap any LangGraph checkpointer with AES encryption, ensuring all serialized state remains protected while maintaining full functionality. The pattern uses PyCryptodome under the hood, and you'll only need to set one environment variable to make it work.
Import SQLite 3. From LangGraph, checkpoint, SERD, encrypted import encrypted serializer. From LangGraph, checkpoint, SQLite import SQLite saver. SERD equals encrypted serializer. From PyCryptodome AES hash reads LangGraph highs key. Checkpointer equals SQLite SQLite 3. Connect checkpoint, DB, SERD equals SERD.
This demonstrates the persistent state pattern with encryption, a critical technique for maintaining execution context across sessions while protecting sensitive data. The pattern combines checkpointing for state durability with serialization encryption, ensuring both continuity and security in workflow execution. What makes this distinctive is its ability to transparently persist complex state graphs while automatically handling data protection through configurable serialization layers. The approach works by decoupling state persistence from encryption concerns through a layered architecture. The checkpointer manages durable storage of execution snapshots, while the serializer handles data transformation and encryption as a separate pipeline stage. This separation allows the system to maintain execution history for features like time travel or fault tolerance, while the encryption layer ensures all persisted data remains confidential without requiring application-level changes. This pattern matters because it solves two critical problems simultaneously: maintaining execution context across interruptions and protecting sensitive data at rest. You'd use this approach in any workflow requiring both durability like conversation threads or long-running processes and security like handling PII or proprietary data. The trade-off is minimal performance overhead for encryption, which is justified by the security guarantees and the ability to resume complex workflows from any checkpoint. Let's break it down line by line.
Import SQLite 3.
Imports SQLite 3, Python's built-in database engine. This provides the local storage backend for the checkpoint persistence layer.
From LangGraph, checkpoint, SERD, encrypted import encrypted serializer.
Imports encrypted serializer, a secure serialization component that encrypts checkpoint data before storage. This prevents sensitive information leaks when persisting conversation state to disk or databases.
From LangGraph, checkpoint, SQLite import SQLite saver.
Imports SQLite saver, a persistence layer that stores checkpoints in SQLite. This handles durable state management between graph executions, preventing data loss across restarts.
SERD equals encrypted serializer. From PyCryptodome AES hash reads LangGraph highs key.
This creates an encrypted serializer using PyCryptodome's AES implementation. It automatically reads the encryption key from the LangGraph highs key environment variable, ensuring secure serialization of checkpoint data before database storage.
Checkpointer equals SQLite SQLite 3. Connect checkpoint, DB, SERD equals SERD.
Instantiates a SQLite saver for persistent checkpoint storage, using an encrypted serializer to secure sensitive data. The SQLite database file, checkpoint, DB, stores execution state between runs, while the SERD parameter ensures all saved data remains encrypted at rest. This pattern combines durability with security for production workflows. LangGraph checkpoint security pattern. This implementation combines SQLite persistence with AES encryption via PyCryptodome, creating a secure local storage solution for graph state management. The encryption key must be set in the environment variable LangGraph HIS key before serialization occurs, or the checkpointer will fail silently during state operations. The SERD parameter bridges the storage layer and encryption layer, making it the single point of control for both persistence and security.
The cipher that locks every door leaves no secrets behind.